Hey there, science fans. Welcome back to another exciting episode where we delve into the wonders of technology and science. Today we're diving into the fascinating world of remaining useful life, or RUL, prediction. This cutting-edge field is revolutionizing how we maintain and manage machinery. Imagine knowing exactly when a machine might break down before it even shows signs of trouble. This isn't science fiction. It's happening right now thanks to advanced algorithms and data analysis. That's the power of RUL. By predicting the lifespan of machine components, we can prevent unexpected failures and optimize maintenance schedules. RUL prediction is a key part of something called predictive maintenance. This proactive approach is transforming industries by reducing downtime and increasing efficiency. Instead of waiting for a costly breakdown, we use data and AI to predict when a machine needs attention. This means fewer interruptions and more reliable operations. This saves businesses time and money and keeps things running smoothly. Imagine the cost savings when you can avoid emergency repairs and extend the life of your equipment. Think about it like taking care of your car. Regular maintenance prevents major issues and keeps everything running smoothly. Instead of waiting for your engine to seize up, you change the oil regularly and get tune-ups. This same principle applies to industrial machinery. RUL prediction is like having a crystal ball for your machines, telling you when they need a little TLC. It's a game changer for industries that rely on heavy machinery. Now let's explore the science behind this amazing technology. RUL prediction combines data from sensors, historical maintenance records, and sophisticated AI models to forecast when a machine part will fail. Sensors placed on machines collect real-time data on various parameters like temperature, vibration, and pressure. This data is then analyzed to detect patterns and anomalies. Data scientists develop complex algorithms that can interpret this data and predict future failures. These algorithms learn from past data to improve their accuracy over time. Machine learning plays a crucial role in RUL prediction. The more data the system processes, the better it becomes at making accurate predictions. With accurate RUL predictions, maintenance teams can plan their work more effectively. They can schedule repairs during planned downtime, minimizing disruption to production. The financial benefits are significant. Companies can reduce maintenance costs, avoid expensive emergency repairs, and extend the lifespan of their equipment. In the end, RUL prediction leads to more efficient operations, happier employees, and satisfied customers. It's a win-win for everyone involved. So, there you have it, folks, the incredible world of RUL prediction and how it's changing the face of industrial maintenance. Stay tuned for more exciting insights into the world of science and technology. Before we can teach computers to predict the future, we need to feed them good data. Lots and lots of data. This data, collected from sensors on our machines, tells the story of their health and performance. But just like a messy workshop, raw data needs to be cleaned and organized. This step, called data pre-processing, is crucial for accurate predictions. We use handy Python libraries like pandas and NumPy to handle missing values, smooth out noise, and transform the data into a format our AI algorithms can understand. Think of it like preparing ingredients for a delicious recipe. We wash the vegetables, chop them up, and measure everything carefully to ensure the final dish turns out just right. Once our data is prepped, we're ready for the next step, choosing the right sensors. You might think that more sensors always mean better predictions, but sometimes less is more. Using all the sensors on a machine can create a lot of noise and overwhelm our AI models. That's where entropy-based sensor selection comes in. Entropy is a fancy word for uncertainty. By calculating the entropy of each sensor's data, we can identify the ones that provide the most useful information about the machine's health. It's like tuning into the right radio station. We want to filter out the static and focus on the channels that give us the clearest signal. By selecting the most informative sensors, we can simplify our models, reduce computational costs, and improve prediction accuracy. Now, let's tackle a common challenge in machine learning: dealing with limited data. Section 4. Not enough data? Let's make some up. Training accurate AI models requires massive amounts of data. This data is essential for the models to learn patterns, make predictions, and improve over time. Without sufficient data, the models can become biased, inaccurate, or even completely unusable. But what if we don't have enough real-world data to work with? This is a common problem in many industries where collecting data can be expensive, time-consuming, or even impossible due to privacy concerns. That's where the magic of synthetic data generation comes in. Synthetic data is artificially generated data that mimics the statistical properties of real-world data. It allows us to create large data sets without the need for actual data collection. Using a clever technique called CT-GAN, we can create artificial data sets that closely resemble our real data. CT-GAN stands for Conditional Tabular Generative Adversarial Network, a powerful tool in the realm of synthetic data generation. CT-GAN stands for Conditional Tabular Generative Adversarial Network. This technique leverages the power of neural networks to generate data that is not only realistic but also highly customizable to meet specific needs. It's a mouthful, but the idea is simple. We train two neural networks to compete against each other. One network, known as the generator, tries to create realistic-looking data, while the other, known as the discriminator, tries to distinguish between real and fake data. One network tries to generate realistic-looking data, constantly improving its output based on feedback from the discriminator. This adversarial process pushes both networks to improve, resulting in highly realistic synthetic data, while the other tries to distinguish between real and fake data. The discriminator's job is to become an expert at identifying fake data, which in turn forces the generator to produce even more realistic data. This adversarial process continues until the generated data is nearly indistinguishable from the real thing. The result is a synthetic data set that can be used for training AI models, testing algorithms, and more. It's like having a master forger create perfect replicas of a valuable artifact, allowing us to study and learn from them without risking damage to the original. This analogy highlights the value of synthetic data in preserving the integrity of original data sets, allowing us to study and learn from them without risking damage to the original. Synthetic data provides a safe and efficient way to explore and analyze data without the constraints of real-world data collection. With synthetic data, we can overcome data scarcity, address class imbalances, and create more diverse and representative data sets. This is particularly important in fields like healthcare, finance, and autonomous driving, where data diversity is crucial for model accuracy, and improve the robustness of our models. By training on synthetic data, AI models can become more resilient to variations and anomalies, leading to better performance in real-world scenarios. Now let's move on to another crucial step: anomaly detection. Anomaly detection is essential for identifying unusual patterns or behaviors in data, which can indicate potential issues or opportunities for improvement. By leveraging synthetic data, we can enhance our anomaly detection capabilities and ensure our systems are more reliable and efficient. Section 5. Spotting the unusual anomaly detection with AI. In today's world, where machines and technology are integral to our daily lives and industries, ensuring their smooth operation is crucial. Anomalies, or deviations from normal behavior, can lead to significant issues if not detected early. This is where AI steps in, offering a sophisticated approach to monitoring and maintaining machine health. Machines, like humans, have their quirks and can exhibit unusual behavior. These quirks might be minor at first, but over time they can escalate into major problems. For instance, a slight vibration in a machine might seem insignificant, but it could be an early sign of a bearing failure. Detecting such anomalies early can save time, money, and even lives. These deviations from the norm, called anomalies, can be early warning signs of potential failures. When machines start to behave unpredictably, it often indicates that something is amiss. This could be due to wear and tear, environmental factors, or even manufacturing defects. By identifying these anomalies early, we can take preventive measures to address the root cause before it leads to a complete breakdown. Anomaly detection is like having a detective on the lookout for suspicious activity. Just as a detective uses clues to solve a mystery, AI uses data to identify patterns and detect anomalies. This proactive approach ensures that potential issues are flagged before they become critical, allowing for timely intervention. We use powerful AI algorithms such as autoencoders to spot these red flags. Autoencoders are designed to learn the normal behavior of machines by analyzing vast amounts of data. They can then identify any deviations from this learned behavior, flagging them as potential anomalies. This process is highly efficient and can handle large volumes of data in real time. Autoencoders are a type of neural network trained to reconstruct their input data. They work by compressing the data into a lower dimensional representation and then decompressing it back to its original form. This process helps the autoencoder learn the essential features of the data, making it easier to spot any deviations. They learn to compress the data into a lower dimensional representation and then decompress it back to its original form. This compression-decompression process is crucial because it forces the autoencoder to focus on the most important aspects of the data. When the autoencoder encounters data that it cannot accurately reconstruct, it indicates an anomaly. By training autoencoders on normal machine behavior, we can identify anomalies as instances where the model struggles to reconstruct the input data accurately. This struggle is a clear indication that something is not right. The autoencoder's inability to reconstruct the data accurately serves as a red flag, prompting further investigation. Imagine trying to fit a square peg into a round hole. This metaphor perfectly illustrates how an autoencoder works. When the data fits the expected pattern, the autoencoder can easily reconstruct it. However, when the data deviates from the norm, the autoencoder struggles, just like trying to fit a square peg into a round hole. The autoencoder would easily reconstruct the round peg, but would struggle with the square one, flagging it as an anomaly. This flagging mechanism is essential for early detection of potential issues. By identifying anomalies early, we can take corrective actions before they escalate into major problems. Anomaly detection helps us identify potential problems early on, allowing for timely intervention and preventing catastrophic failures. This proactive approach not only enhances the reliability and efficiency of machines, but also ensures the safety of workers and the environment. Early detection and intervention can prevent costly downtime and extend the lifespan of machinery. Now let's dive into the heart of RUL prediction. Building the prediction model itself. This involves using advanced machine learning techniques to predict the remaining useful life of machinery. By accurately predicting when a machine is likely to fail, we can schedule maintenance activities more effectively, reducing downtime and optimizing operational efficiency.